We have already seen this object diagram before. This object diagram for the social network corresponding to the class diagram shows 4 profile objects. The profile objects Putin, Merkel, Trump and May, and the object diagram shows 5 subject objects, namely the objects horses, hairstyle, opera, shoes and OCL. And the intention is that profile objects or persons standing behind the profiles can express interest in particular subjects. So, for example, the profile May, standing for Theresa May. The profile May is connected through the interest association to the hairstyle object, to the opera object, and to the shoes object, and that's their interest. Another use of OCL, we have seen the use of OCL for class invariants. Another important use of OCL is to state queries. We have such a complex, simple, whatever system state object diagram, and now we are interested in particular facts that hold in this system state, and OCL can be used to formulate queries against an object diagram, or in other words, an OCL expression, an OCL query like this here can be evaluated in an object diagram and gives back a particular result depending on the query that you pose. The query that we see here is the query profile all instances, select p.subject includes opera. Roughly speaking, in English terms, well, I want to know those profiles where the profile is interested in the subject opera. And the answer is here, for this query, the answer is a set of profiles, namely the set May Merkel, because, well, you can look here at the opera subject and you see that opera is connected to Merkel and opera is connected to May. Yeah, and for example, neither Putin nor Trump are in the result here. We have seen before the option all instances applied to a class. This gives the current objects associated with the class, so the current profile objects. We have seen select before. For select, you formulate inside the select a predicate that the source objects must fulfill in order to be in the result of the select. And the predicate that is formulated here is what you see here. We make use of one given object, namely the opera object, and we navigate here from a profile object through the role name subject to all the subjects that are associated with the respective profile objects, and we consider only those profile objects which have in their associated subject set the term opera. So you can imagine, or you can think of, that this P sort of iterates over all these objects, and we select those objects for which this formula inside the select is satisfied. One part of the formula is that we do the computation here, p.subject. So for example, we would have to consider that the p is equal to Trump. Then p.subject is equal to set hairstyle. And if you consider May, then p.subject, p.subject for p equals to May. So May subject is a set consisting of 3 elements, namely hairstyle, opera, and shoes. This subject comes from the class diagram. Let's jump back. So this role name here is used in this query here. Okay, so that's another important use of OCL. And the object diagram is interesting insofar that we see here a many-to-many, a star-to-star multiplicity. We see it insofar we have one profile object may be associated with different subject objects, and one subject object can be associated with different profile objects. So this star here refers to the multiplicities star coming from the class diagram. Okay, so far we have looked at the class diagram and we have looked at the object diagram. Let's look at another form of diagram that is available in UML, and that's the use case diagram. The use case diagram is typically applied in early phases of software development, for software, in the early phases of software modeling, typically in the requirements phase. The use case diagram, this is a use case diagram that we can think of that is applicable to our social network. In the use case diagram, one has actors. These are the strawmans here. There are use cases. These are the ellipses. And there are relationships between the use cases, which are indicated in this diagram by dashed lines or with an arrow. And on the dashed lines we see an include or an extend relationship. The formal term for this syntax here is that include and extend is a stereotype. The use case diagram is not supported in use. It would be nice to have it, but currently it's not supported. What is the basic intention of the use case diagram? The basic intention is you have a complete system. This is a complete system, and you have actors in the system, and these actors perform particular functionalities, and these functionalities are called use cases. A use case is a specification of an action sequence, as it is said in the book by Rambaud, Booch, and Jacobsen. And a use case can have attributes. You see it, for example, here, the register use case. For performing the register use case, which is responsible that a user becomes registered in the social network. And you see here, not only the user is involved in this use case, but also the admin of the social network. And for performing this functionality register, particular attributes have to be provided, namely the first name, the last name, the username of the user that is going to be registered, and the subject set that the user is interested in. And there are other functionalities. So one functionality is here check friendships, and that's a functionality where only the user is participating in, and there's another functionality here, post and comment. That's also only a functionality where also only the user is participating in. Both the check friendship and the post and comment functionality are connected to the login. And in the login, you see here another, login is another functionality here in this system. And the login has an attribute, and that's the username. In order to log in, the username has to be specified. The login functionality, the login use case, is a use case that is included in the post and comment use case, and the login is included in the check friendship use case. Include means the inclusion is mandatory and the inclusion takes place once. There's another relationship between functionalities, another relationship between use cases, and that's the extent functionality, the extent relationship, the extent stereotype. We see here when we consider the check friendships use case, we see that check friendships use case can be an invite use case, it can be the accept use case, or it can be a decline use case. And in contrast to the include relationship between use cases, these three are marked with extend, and that means the inclusion, the consideration of the subordinate use case is optional, and it is repeatable. So with include you have mandatory, with extend you have optional, with include you have it is done once, and with extend it is repeatable, it can be done several times. There's another actor in this use case diagram, that is here the content inspector. When the user has posted or commented particular thing, so she or he has published a posting. The other option here is to search postings and to comment postings. Well, the content inspector is an actor that checks the postings and the comments, whether they are aligned with the legal laws that have to be obeyed, and maybe they are removed. These postings or these comments are removed. So that's the role of this content inspector here. So the general idea about the use cases is that you have a general overview on your system, in this case on your social network. You have the actors that change the system state of the social network, and the actors can perform are connected to particular use cases, and by performing these use cases the system state changes. The next diagram is the state chart diagram. Again, this slide shows an example and mentions the concepts of the state charts. State charts are there for specifying the behavior In particular, in use, they are applied for determining so-called object life cycles, and the state charts that are used here are so-called protocol state machines, and they determine these protocol state machines, this special form of state chart diagrams determines operation call sequences. Let us have a look at the state chart, at the protocol state machine for the central class, for the profile class. For the profile class, we see here in the state chart, the operations that can be executed by a profile object. So we have the init operation, we have the invite operation, accept, decline, publish, and comment operation. We have more operations in the class. Not all operations from the class occur here. So the state chart here makes a statement about the order of the mentioned operations. And what is determined here is the following. We determine the life cycle for each single profile object. The life cycle of each single profile object has to start with the creation of the object. Then the operation init has to be performed, and then either an invite, an accept, a decline, a publish, a comment can be executed by the object, provided the pre and post conditions, the operation contracts are satisfied. We will see operation contracts later. But in principle, these state charts determine object life cycles. So here in the state chart, in the state machine on the left-hand side, we restrict the life cycles first an init and then one of the 5 operations here. And there you see here there is a loop here from this state to itself. We have the states firstborn, so after we have an initial state here, that's the state prenatal. Then the create happens, the profile objects get into state born, and then the init happens and we are in state living, and we have a cycle here on the state living. One of these operations can happen. In the states, we have states here. On this side we have 3 states: the state prenatal, the state born, the state living. And we have state invariants. These are OCL expressions which have to be valid in each state. So when we are in the state born, the username of the profile object has to be the empty string. And when we are in state living, the username of the profile object has to be unequal to the empty string. So we can make precise the states by putting here state OCL expressions, state invariants that characterize the state. OCL state invariants are optional, as you see, for example, here on the second state chart. And you will see also here on the second state chart, that's the state chart for the class friendship. The class friendship has 2 operations, accept F and decline F. And in contrast to this sort of infinite loop here on the left-hand side, the state chart for the friendship class is quite restricted. After the friendship object has been created, it is in state pending. The friendship is in state pending. And then we have an alternative. Well, the friendship can be accepted, then it is in state accepted, or the friendship can be declined, then it is the friendship is in state declined. And this symbol here means that we have reached a final state. This is a symbol for the final state. As you see here, there are no, as you see here, you see nothing. There are no outgoing edges. And so in the state accepted and in the state declined, no operation calls are possible anymore for the friendship object. So this is quite a limited life cycle for the friendship object. There are exactly two complete life cycles, namely create accept or create decline. So we have seen the states, we have seen the state invariance, at least we have taken a glimpse of it. We have seen an initial state, we have seen a final state or two final states over here. Final states are not mandatory. You do not have to specify here a final state. And we have seen the normal states that can have a state invariant and do not have to have a state invariant necessarily. The state transitions in the general form of the state transition is a form guard, event, postcondition. And what we see here is only on the events, we only see an event which is an operation call, and we do not see any guard and we do not see any postconditions. We will see examples for this later. So, main message, state charts determine object life cycles and in use and in UML protocol state machines which determine operation call sequences are available. On the use shell, on the use command line interface, we can execute commands. We have seen this before. We have stated query, we have evaluated numerical expressions. But what is also possible, we can execute particular commands. We can, for example, create objects, so we can do object creation. We can perform particular operation calls on objects. We see here the call init on the object Merkel, which was created one step before. We can use variables on the shell. Yes, we see here a variable which is given, which is assigned something as a result of an call to an operation, and we can access the variable. This variable p that is assigned here on the use shell is used later in this with this statement here. So this P is used over here. This series of commands, this command sequence, is exactly the command sequence that generates this object diagram, or that generates this object diagram here. We could count. We are counting. We are creating here first three objects, three profile objects, Merkel, Putin, Trump, and we have a fourth object here, the May object, and then we are doing the initialization of the profile objects. That's the call of the init operation. Merkel is initialized with the values Angela, Merkel, and the username Mutti. And Putin is initialized with the first name Vladimir and second name Putin and username Crab, and so on and so on. Object creation, operation calls, variable assignment, and access. And as I said before, this command sequence generates this object diagram. It does not yet generate these objects. There are no subject objects right now and no interest links. So this sequence of operation calls, this command sequence, is what we call in use a scenario or a test case definition. With this we generate object diagrams that can be used for testing purposes, and well, you can understand this command sequence is here as one particular test for the model that we have developed. So the result of this command sequence is the object diagram, but the command sequence here can also be documented in other forms, namely in form of a sequence diagram and in form of a communication diagram. We see here in this sequence diagram, we see the starting part of this test case, of this scenario. We see the starting part in the sequence diagram. So we see here partly the objects and partly the profile objects and the friendship objects. And the sequence diagram here reflects the operation calls that have been executed, and the sequence call and the sequence diagram also reflects the operation calls which are induced by particular other operation calls. So for example here the decline trump operation call induces another or calls another operation call. That's a decline in the profile class, and the decline f is an operation in the friendship class. First, the general idea here is this sequence diagram, the starting part of the larger example, are the first statements, the first commands from the previous one, namely exactly we have here the Putin decline, and then we have something else which is also happening. So the sequence diagram reflects this scenario up to this part. So this is the part of the test scenario that is reflected here. Each object is represented with what is called a particular lifeline. And on the lifeline you have particular activations here where an activity is going on in the object. And typically an activity is going on after a message has been sent to the object. So yeah, this is a point when the Merkel object receives the operation init with these parameters, and this changes something in the object. And analogously, another operation call is here the decline trump. The decline trump, this is an operation which is issued by the Putin object, and previously Trump has invited Putin to become Trump. So let us look at these two operations here. That's the invite, which is issued by Trump, and the decline, invite Putin, which is issued by Trump, and the decline Trump, which is issued by Putin. That means Trump has invited Putin to become his friend, but Putin has declined the friendship of Trump. Yeah, again, we see these two commands here in the command list, which can also be depicted here. And the overall effect, we see the overall effect here in this part of the object diagram. Trump has issued the invite, and therefore he is the inviter and Putin is the invitee. And after Trump has invited Putin, the friendship is first pending, and after Putin has declined the friendship becomes declined. This is also reflected partly here in the state chart diagram for the friendship. So the friendship object, after the create, the friendship object that was initiated, that was created through the invite that has been done by Trump, the friendship is in state pending, and after the decline by Putin, the pending friendship becomes a declined friendship. So this is this dynamic behavior that we see here in the sequence diagram, and the sequence diagram can picture these executions, these test cases in an overview form. There's a second alternative. There's an alternative to displaying test scenarios. An alternative to the sequence diagram are so-called communication diagrams. In the communication diagram, you also have objects. We have the Merkel object, we have the Putin object, we have the Trump object. We also have the objects, the friendship object. We have a friendship 1 between Merkel and Putin. We have a friendship 2 that is between Putin and Trump. And one of the main differences here between the sequence diagram and the communication diagram is in the sequence diagram we have a geometric ordering here of the messages, and this ordering of messages, which is geometric in the sequence diagram, is captured here by a numerical system. So first we create the Merkel objects at message number 1. Second, we create the Putin objects, that's message number 2. Message number 3 is a creation of Trump. And for example, the invite here the fact that Trump invites Putin is represented here by the message number 8. This is the invitation of Trump to Putin, and the fact that Putin declines the invitation is done here, or is reflected here by message number 9, which is a decline of Trump's invitation by Putin. So in this communication diagram, we again have objects, we have messages which are placed on connectors between an actor. The general actor here is the same as the general actor here in the sequence diagram. So in the communication diagram, we have objects, we have messages, we have message numbers, and we have a link representation which is close to objects. Basically, this have been the diagrams which are supported by USE. There's one important diagram that I want to mention here. That's the activity diagram that is not supported in USE. With the activity diagram, again, here we see an example and the main concepts of the activity diagram. With an activity diagram, you can specify and detail what happens inside an operation. So we see here for the class profile, we have the operation init. Let us jump back to the class diagram. Yeah, in the class profile, we have the operation init, and this is detailed here in the activity diagram. This is the representation of what happens in the operation init in forms of an activity diagram. It is not supported, the activity diagram is not supported in use. We have an alternative here for describing what is going on in an operation. In use, we have a language that is called SOIL, Simple OCL Imperative Language, that uses OCL expressions in a lot of places and is sort of a programming language. And with this language, you can explicitly say what an operation is doing. And what the operation init should do is, well, the operation init has three parameters: a first name, a last name, a username, and these three parameters are assigned to the self object. That means the self object is the object on which the operation init is called. And yeah, there is a one-to-one correspondence between these three attributes and these three parameters here. As an activity diagram, you can specify it in form of this graph. So this sequence of actions that is going on here is reflected here by an initial node, by a final node, and then some action nodes in exactly this order. An alternative, and this activity diagram directly represents this SOIL operation. There's one particular case here in this example, namely the order of the assignments can be chosen here in an arbitrary way. We have three assignments, and you can do the assignments in. We have done it here in the way the starting assignment is on the first name, last name, and then username, but you can do it in any order because the assignments are not dependent on the right hand side are independent of each other. And this can be reflected. Reflected in as an activity diagram with a special features, with a fork node and with a join node. This is an alternative specification of what is going on here. It's a different. It has a different semantics than this here. This is a strict sequential order. Here, the activities are split. The fork nodes splits the activities, and the join node brings together the activities again. And the fact that these assignments can be done in any order is reflected in this activity diagram. We have the same action nodes here, but the order is different. So this activity diagram may be implemented like this here, or it may be implemented in the exactly opposite order. We are nearly done, but before closing this part of the course, I would like to bring together the bits and pieces that I have been talking about here in the first part. So, important basic diagrams in UML are the class diagram, which determines the basic structure of your system. With a use case diagram, you can get a good overview on the system by specifying your requirements and the functionalities that your classes, your objects should have. With object diagrams, you can specify particular states, and you can look into the details of the states, for example, with OCL queries. The state chart diagrams determine the order in which the operations from the class diagram can be executed. When you have an execution, when you have a test case, then with the sequence and communication diagram, you can visually represent an execution, and sequence diagram and communication diagram are brought together under the label of interaction diagrams because you show interacting objects in these diagrams. With the activity diagram, you show the activity that is going on in a single operation. In our approach in use, we use this programming language SOIL, simple OCL imperative language, for this purpose that the activity diagrams are for. Another criterion for distinguishing the diagrams is whether they deal with structure or they deal with behavior. Yeah, and you see here the classification. Class and object diagrams basically deal with the structure, and use cases, state charts, and interaction and activity diagrams deal with the behavior. The diagrams are enriched and made precise by expression written in the object constraint language. There are a lot of uses of OCL expressions. We have seen uses in the class diagram for expressing invariants. We have seen uses in state chart diagrams for expressing state invariants. You can use them in object diagrams for expressing queries, and we will meet and see other uses of OCL, and many of these things that I have mentioned, many, if not all, are doable, are traceable in our tool use in the UML-based specification environment. Thanks for your attention.